I want to go through how to do this FRQ from 2004, the Form B FRQs. This is the 6th question involving area, and I think this FRQ is particularly difficult. It definitely took me a couple tries to understand it, but I'm going to go through how to do it today. So the question says, let L, which is this line here, be the line tangent to the graph of y equals x to the n at the point 1, 1, where n is greater than 1 as shown above. So I'll just write n is always greater than 1. Part A says, find the integral from 0 to 1 of x to the n dx in terms of n. So this part isn't too hard. We just need the integral from 0 to 1 of x to the n dx. So this leaves us with x to the n plus 1 divided by n plus 1 from 0 to 1. And we have 1 to the n plus 1 over n plus 1 minus 0. But 1 to the anything is just 1, so we're left with 1 over n plus 1. Okay, now for the more difficult parts of the problem. Part B. Part B says, let T be the triangular region bounded by L, the x-axis in the line x equals 1. Show that the area of T is 1 divided by 2n. So let's look at this. It's telling us that the area T is triangular. So that can help us because they told us that the area of T is 1 over 2n. So I'm going to say that 1 over 2n has to equal 1/2 times the base times the height, which is the area of a triangle. But we know our height is 1 because this goes up to 0.11. So the only unknown we have is just b. So I'm going to cross out h and say that 1 over 2n has to equal 1 over 2 times b. So therefore, b has to equal 1 over n. But now let's actually prove this. So we know that the base of this triangle is this region right here. And we know this is at 1 and this is at some point p. So we need to solve for what p equals. What we do know, though, is that L is a line. So any line, you could find an equation for it as long as you have a point, which is 1, 1, and a slope. And so though they don't tell us our slope, we do know that L is tangent to the graph x to the n at the point x equals 1. So I can use that to solve for the slope. So I'm going to say that y prime equals, well, it would be n times x to the n minus 1. And we want this when x equals 1 because that is the point at which L is tangent to this graph. So I'm just left with the derivative being n. And so, therefore, the slope of L equals n. So let's use this in our equation. We can say that we're going to use y equals mx plus b. So we know that y equals nx plus b. And if we plug in the points 1 and 1, we get that 1 equals n plus b. So b equals 1 minus n. So then we can say y equals nx plus 1 minus n. But we want to know what x equals at this point because by solving for this x value, that's really the point p that we're looking for. So I'm going to say that when y equals 0, x is p, so we're going to use the point p comma 0. So I'm going to say 0 equals n times p plus 1 minus n. So to solve for p, I'm going to rearrange this so I get n minus 1 divided by n equals point p. So that's our point. And we know that our base, this region that I shaded here, is equal to 1 minus point p, because if you think about it, you go all the way out to 1, and then you subtract this point p. So let's do that. So I'm going to say that the base equals 1, doesn't look like a 1 minus n minus 1 divided by n. I'm going to change colors because I think that yellow is a bit hard to see. So therefore, I get that n over n minus n plus 1, I'm just going to distribute this negative, divided by n equals our base. And so then I get that the base equals 1 over n. And so this actually is what we were looking for. That's what we wanted to prove. So because our base equals 1 over n, we know that 1/2 times base times height equals area of t, I'll say. And our height just equals 1 because of the point they gave us. So then I can say that 1/2 times our base, which is 1 over n, equals the area of t. And you're just left with 1 over 2n equals 1 over 2n. And so that is our proof for the area of t being 1 over 2n. So now part C, I'll do this green color. Part C is asking, let S be the region bounded by the graph of y equals x to the n, the line L in the x-axis. Express the area of S in terms of n, and determine the value of n that maximizes the area of S. So there are really two parts to this section of the problem. So I'm going to start with the first part, which is express the area of S in terms of n. So let's take a look at our graph. So this is the area of S. I realized that my line got deleted. We're going to want to find this area that I've just shaded in. But the thing is, we can't do this super nicely because L, this point P, comes from a line that's on a slant. And so we can't use point P as a limit of integration. But what we can do is we can say that the area of the total, and then subtracted from the area of T, which we just found, equals S. So I'm going to use that. So I'll start by writing that the area of S equals total area minus area of T. So let's specify this. I'm just going to write S equals, well, our total area is what we solved for in part 1. That's just the integral of x to the n from 0 to 1. So as you see here, that equals 1 divided by n plus 1. So I get 1 divided by n plus 1 minus, and then the area of t, which is 1 over 2n, equals S. So that is the area of S in terms of n. And so now we need to maximize this. So I'm going to say, this is an optimization problem whenever you hear the word like maximize or minimize or like the most. Words like that should trigger optimization in your mind. And so whenever we do an optimization problem, we start with an objective function and then we have some sort of constraint. So my objective function is the area of S, which is S over 1 divided by n plus 1 minus 1 over 2n. And then my constraint in this problem isn't super important. Our only constraint is that n will be greater than 1, which I know because they told me that earlier in the problem. And I'll write over here that we want to maximize this area. So we need to take the derivative of s. But one important thing to note in this part of the problem is that we need to take the derivative with respect to n. Whereas above we were taking derivatives with respect to x, we've now changed the unknown in the variable that we're trying to maximize to n, which is why we're going to derive with respect to n in order to then maximize n. So let's do that. I'm left with s prime equals negative 1 over n plus 1 squared plus 1/2 n squared. 1/2 divided by n squared, I should say. So that is my derivative. And something is, in order to find when something is maximized, we have to set it equal to 0 when it's at like the top of the mountain. So what I'm trying to solve for is when 1 over 2n squared equals 1 over n plus 1 squared. I just rearranged my problem a bit. So really what I'm looking for is when does 2n squared equal n plus 1 squared. So I'm going to start by factoring this out, and so you're left with 2n squared equals n squared plus 2n plus 1, and then I'm going to subtract everything over, and I get n squared minus 2n minus 1 equals 0. But as you can see, this won't factor, because if I have negative 1 and positive 1, you're not going to be able to factor this, and the quadratic formula isn't going to work for us at this point, so I'm going to complete the square. So I get n squared minus 2n equals, and then add the 1 over, equals 1. If I do negative 2 divided by 2 squared, I get to add 1 to both sides. So I get n squared minus 2n plus 1 equals 2. So this breaks up into 1 and 1, or negative 1 and negative 1, I should say. So n minus 1 squared equals 2. If you then take the square root of both sides, I'm only going to pay attention to the positive square root because of this constraint that I had where n is going to be greater than 1. So the negative square root is kind of like an extraneous answer. So you're just left with n minus 1 equals root 2. So then n equals root 2 plus 1. And that is the value that will maximize, that is the value of n that will maximize the area of S. I hope this video helped you with this problem. It definitely took me a few tries to really understand this problem, and don't worry, because this type of problem with the two areas doesn't really ever come up again. I think they probably realized that people didn't understand this when they did this FRQ. But I hope this video was helpful, and I'll see you in my next video.